Hey, ladies and gentlemen, thanks for coming back again and trying to stay awake again for another exciting video in General Chemistry 1. The topic is naming compounds. Binary compounds means there are two elements, two elements in the compound. Some of them are salts, some are not salts. How do you know if it's a salt or not? Oh, here we go. If I combine any metal, which are all the yellow ones, with any non-metal, the red ones, I get what you call a salt. This is my rule of thumb. It usually works, almost always works, except for a few ammonium salts and other oddballs, but for the most part. But if I take two non-metals in the red and bind those together, I get what's called a molecule. And they're sharing electrons. We'll talk a whole bunch more about this in the next chapter or two. But for now, if I have a metal and a non-metal, the metal likes to lose electrons, become positively charged, and the non-metal likes to gain electrons, become negatively charged. So in essence, they trade electrons, transfer electrons. They don't trade; they transfer from the metal to the non-metal, and yeah, you get a salt. What we call a salt. What a chemist would call a salt. Yeah. So I think we've seen this before, actually, in lecture, but let me show it to you again. Here's a cool table describing some of the typical predictable charges of many of the elements. Everybody in this first family loves to become a +1 charge, to lose one electron. These guys like to become a +2 charge, lose 2 electrons. We skip these for a second and come over to the boron aluminum family. Those like to lose 3 electrons. Carbon would like to lose 4 electrons to become a +4, or it could easily 1, 2, 3, 4 gain 4 electrons to become like neon. So carbon and nitrogen and phosphorus and silicon are all so flexible. They can do whatever anybody else asks them to do with any coercion. But fluorine and chlorine and bromine, they love to get a -1. Same for iodine, oxygen, sulfur, selenium, tellurium. Love to become a -2, gaining 2 negative electrons, gaining 1 electron. Of course, this is called the zero column. The metals in the middle, the transition elements, they're quite variable and difficult to predict. For example, vanadium could be a vanadium 2+, having lost 2 electrons, or it can lose 3 electrons, or 4 or 5. And we designate that with a Roman numeral. I can see how vanadium could lose 1, 2, 3, 4, 5 electrons to become like argon in its electron configuration. But it really wouldn't want to lose any more than that. Iron can lose 2 or 3. Copper can lose 1, but almost always 2. Zinc almost always 2. Silver almost always 1, losing electrons. Tin and lead actually behave the same way, but they're not actually transition metals, but we still should use Roman numerals to describe their oxidation state, how many electrons they've lost. Tin likes to become a 2+ or a 4+, same for lead. Lead Roman numeral 2, lost 2 electrons. Lead Roman numeral 4, lost 4 electrons. So we can kind of group the following naming schemes into a couple of categories. In the first category, called type 1 binary, I have a metal and a non-metal, but the metal has a predictable, typical, usual, almost always charge. So these elements over here, almost always the same charge, +2, +3, +3, +1, +1. +1, +1, +1, +1, +1, +2, +2, +2, +2, +2, and because they're all so predictable, I don't have to mention with the Roman numeral what the charge on the metal is. So I'll combine a metal from here, purple, with a non-metal from red. Or a type 2 involves combining one of these metals, the transitions, which are quite variable, in which case we will use the Roman numeral to tell what the oxidation number is in the name and non-metal. But if I go with the type 3 binary, I'm just talking about a molecule, talking about covalent bonds, talking about sharing electrons. So any of these, I also included xenon because it's kind of large and can react with fluorine if you push it hard enough. I guess these inner transitions belong to that type 2 salt classification as well. Sorry, I got distracted there by a knock on the door. Oh yeah, so type 1 binary. I take a metal and a non-metal, and I don't have to mention the charge on the metal because it's so predictable. It always has the same charge. Lithium, sodium, potassium always have a +1. +1, +1, +1. So if I combine a first family metal With any nonmetal, I can just name it lithium fluoride, change the fluorine to fluoride, sodium iodide, potassium oxide. Here I see the oxygens in the 2- family and potassium's in the +1 family. So, in order to make the 2 minuses balance out with 2 pluses, I took 2 potassiums, 2 pluses for the 2 minuses. Rubidium's in the +1 family as well, so I put rubidium 1+. But nitrogen's in the family that loves to become a -3. So I called it nitride, not nitrogen, but nitride. And nitrogen's in the 3- family. Because I have 3 minuses, I took 3 pluses. This is 3 rubidiums, 3 single pluses to balance the 3 negative of that single nitride. Magnesium chloride, calcium bromide. You see, it's quite easy, isn't it? Naming, it's just aluminum sulfide. Silver selenium becomes selenide. Zinc chlorine becomes zinc chloride. The challenge is sometimes observing the charges. Silver is a +1 almost always. Selenium's in the oxygen family, loves to become a 2-, gaining 2 negative electrons. So if I want the pluses to balance with the minuses in a neutral compound, the neutral salt, one formula unit has 2 silvers and 1 selenium. Oh yeah, here's a tricky one. Aluminum's in the 3+ family, sulfur's in the 2- family. How do I make a 3+ and a 2- balance out? Well, if this is 3+, I take another one of these. 2 of these would be a 4-, but that's too many minuses. So I take another one of these, and that's 6 pluses, but that's too many pluses. So I come back here and take another one of these, and that's a total of 3 of these. That 3 times -2 is -6, and 2 of these, 2 times +3 is +6, and that balances out the salt. I know that's pretty quick, but you have the benefit of rewinding and asking questions of your TA and looking at the PDF document. Type 2 binaries, a little more tricky because the oxidation number can be pretty much almost whatever. Although iron likes to be a 2+ or a 3+. So here's an iron 2 compound, here's an iron 3 compound. Hang on a second. So for type 2s, I have a Roman numeral almost always with that metal. It might be a transition metal, it might be tin or lead or something that needs a description of what the oxidation state is. So I called this iron 2 chloride because here I have 2 chlorines and those love to be a -1. So what does that force iron into being? 2 of those would mean I have a 2 negative overall, so this has to be a 2 positive. If I said the formula FeI3, that means 3 iodides, 3 iodide ions, and 3 negatives force the iron here to be a 3 positive, and that's how I decided it was iron 3, not iron 2. Vanadium 4, that means a 4+ on the vanadium. Fluoride's a single minus. 4 negatives, 4 positives. That's a tricky one. Vanadium 2 phosphorus becomes phosphide. Phosphorus, nitrogen in the family like to become a -3, pick up 3 negative electrons, so that's a 3-. I decided this should be a vanadium 2 because the 3-2, this is so stupid. You ready for this? I call it the 3-2 switcheroo, or the 2-3 switching trick, where I take 3 of these and 2 of these. 3 times +2 is 6 positive. 2 times -3 is -6. 6 negative and 6 positive balance out, so that's called vanadium 2 phosphide. Cobalt 2, oh, that's a typo. Holy moly. I got to change that to a 3. I will change that to a 3 before I post this PDF. My bad. Yeah. Cobalt 3 bromide would be 3 positive there and 3 negatives here. Jeez, that's embarrassing. I'm going to take that off the screen as soon as I can. All right, I'll change that. Copper 1 oxide. Copper 1 is pretty rare actually, but I put a copper 1, and oxygen's a 2- in the 2- family. So how many positives do I need if I have 2 negatives? I need two positives. So I took 2 single positives. This is copper 2 sulfide. Sulfur's in the same family as oxygen, both the 2-. But if that's a 2-, that must be a 2+ to make it balance 1-1. Tin 4 oxide. Yeah. So oxygen's in the 2- family, so 2 times -2 is -4. That must be a +4. Tin 4. Continuing. My goodness, goes on for a long time. Here's a tin 2 compound, tin 2 iodide. Tin 2+, that's a 2+ there. And I have 2 iodides to balance out the 2+ of that. Lead 4 telluride, or telluride, I can't pronounce that correctly. Lead 4, so Te is in the oxygen family, and it looks to be a -2. I decided that would probably force the lead to be a 4 plus to make the charges balance out. Here's a 3-2 switching thing again as well. 3-2, that must be a lead 2 to make the nitrogen, which is usually a 3 minus when in a binary compound. Mercury does a really weird thing. I hesitate to show you this one, but I'm going to. Mercury 2, no problem. This is mercury 2 chloride. Same as always. But a mercury 1 ion is really weird. It hooks up with another of its type, and it's called a dimer. Di means 2 units. That's called a mercury plus, mercury 2 plus. And so I'll just say that's very weird. So here's the formula for mercury 1 chloride. It seems like you should just reduce that 2 and that 2 to be HgCl. And you can, but the proper term is like this. Here's uranium in the inner transitions. Called that uranium 6 fluoride because fluorine's a -1. And that would force the 6 -1s to be 6 positive on the uranium. Let me look briefly at type 3 binaries. We use these prefixes mono, di, tri, tetra for these all nonmetals, 2 nonmetals put together to make a molecule. And over here I listed the oxidation states. Nitrogen monoxide, 1 nitrogen, but we don't say mononitrogen monoxide, we just say nitrogen, meaning implying 1, monoxide telling that I have 1. And that must be a 2 plus and a 2 minus. Remember, a 2 minus and a 2 plus. Oxygen is very electronegative and pulls its electrons to be a -2. That forces the nitrogen to be a +2. But if I change it just a little bit, nitrogen dioxide, 2 times -2 is -4. That forces that to be a +4. Same story for the dinitrogen tetraoxide. Di means 2 and tetra means 4. So the prefix goes with what comes after it. Tetraoxide means 4 oxygens. Here's a whole slew more if you care to take a gander. Dinitrogen monoxide, 2 nitrogens, 1 oxygen. -2, +1. 2 times +1 is +2. Carbon dioxide, charges balance. Carbon tetrachloride, chlorine's in the -1 family. 4 times -1 is -4. That makes the carbon must be a +4 oxidation state. Sulfur hexafluoride. I'm seeing some patterns. Xenon hexafluoride. Tetraphosphorus. 4 phosphorus is decaoxide. Sometimes that A is dropped, called decoxide or decaoxide. Oh yeah, this is a weird one. 10 times -2 is -20. So 4 times positive what gives you +20? Phosphorus here's in the +5 oxidation state. Diphosphorus pentoxide or pentaoxide, arsenic tribromide, dihydrogen monoxide, water, just kidding, but yeah, its real name is dihydrogen monoxide, if you're technical about it. Nitrogen trihydride, I gotta go check this. I think this is the right oxidation state. I might be wrong, and if I'm wrong, I'll change it on the PDF. But hydrogen usually likes to be a +1. That would force the nitrogen to be a -3. That would make sense to me, but I'm not so sure if I'm right on that. Tellurium monoxide. This is a semi-metal almost, but it's still a -2 +2 combo. Oxygen is more electronegative. It gets its -2 from the tellurium and forces it to be a +2. What about the polyatomic ions? We say, what if I have a metal combined with some other combo, non-metal combo? So here's ammonium ion and sulfite ion. You should know these ions. Sulfite's more rare than sulfate. This is a very common one, but one less oxygen than sulfate is sulfite. Iron 2 sulfate. Copper 2 phosphate. Why is that a copper 2? There's 3 there. I know. I have 2 of these, so that's a -6. This has to be a +6, so I took 3 of those. It's a tricky process. Some students take a long time to practice with this. Good idea too. Zinc nitrate. You should know these polyatomics. Acetate, you should probably know that one. Nickel 2 acetate. Magnesium's a type 1. It's always a +2. Magnesium permanganate. Permanganate's weird because it has a metal also with a non-metal, but it's a polyatomic anion that you should know. Aluminum dichromate. Vanadium chlorate. You should know chlorate. You should know hydroxide. Platinum hydroxide. Platinum. Oh, goodness. Should that be a platinum too? I better look that up. I think it might. I better include a Roman numeral there as well, because platinum's a transition metal. I should call that platinum 2 hydroxide. I'll change it on the PDF. All right, and a few other last minutes. By the ways, oftentimes when these salts are formed with a metal and a non-metal, or metal and some polyatomic non-metal combo, I'll have some water that's joined up along with the crystal in its formation. Perhaps because of the way it's formed, or perhaps it even absorbs it from the air sometimes. Copper 2 sulfate pentahydrate. Guess what penta means? 5. Cobalt 2 chloride hexahydrate. So that times doesn't mean to multiply. It means that we just have some waters associated with it. So 2 waters associated with this nickel 2 chloride, and 7 waters associated with this magnesium sulfate. Yeah, magnesium sulfate. Whew, man, I talked too fast. But rewind, watch, ask. Thanks, guys. See you in class.